All right, welcome to Module 12 in Unit 3. So today we're going to talk about the cerebral cortex. So that is our highest level, our most evolved part of our brain. So here are the learning objectives and the vocab. So let's first define what cerebral cortex is. So our cerebral cortex is like this thin, intricate layer of the brain that covers the two hemispheres. It was actually I think the original name comes from the word bark, meaning like a tree bark. So it's like covering the hemispheres. So this is our highest level in our evolved human brain. So if we go back to our hand mnemonic, I'm going to call it. So we're going to do this, right? So we have our brainstem and spinal cord, and then we have our limbic system, and at the highest level, we said the cerebral cortex. So this module is all about the cerebral cortex, that higher level, most evolved thinking. So if you were to roll out the cerebral cortex, it would be the size of a large pizza. But our skull is what it is, so it's all wrinkled and shaped like that so that it can fit in our brain, in our skull. So I know you thought you were all done with cells, but we need to learn about glial cells, because glial cells are the little worker bee cells for all of our other neurons. They help support, nourish, protect our neurons. And actually, Einstein, they found that his brain was the same size as average human's brain. It wasn't any larger as they once thought it might be, or anyone who was intelligent thought it would be larger. But they found that he had more glial cells. So they are also kind of thought to be connected to thinking and learning. We're still learning about all of these things. Obviously, we're constantly learning about the brain, but the more complex the organism, the more. So when they were first studying the brain, they first broke it down into 4 main lobes. So this is a very simplified explanation of the functions of the brain. However, we still use these terms today when we're talking about that larger part of the brain. We know that within these lobes, there are multiple functions and specific parts do specific things, but we still refer to these 4 lobes that you do need to know. So, frontal lobe. So when you think frontal lobe, go like this, like you're thinking. So planning, decision-making, thinking, that all comes from our frontal lobe. So parietal lobe is up here. So when you're washing your hair, you are touching your parietal lobe. So parietal lobe is for touch, like when you shampoo your hair, you're touching here. And then occipital lobe, so I want you to think about being hit in the back of the head, and then you see stars, right? Have you heard that before? So that is because our occipital lobe is in the back of our brain. So when you think occipital lobe, seeing stars. And then the last one, the temporal lobe, which is right above our ears. I want you to think about keeping the tempo, right, to music, and that is right above our ears. So the motor cortex, that is in our frontal lobe, and you want to think voluntary movement. So brain surgeons have been able to map the motor cortex. So this little guy here is homunculus, and he actually is kind of showing us where we have more precise control and also where we are more sensitive to touch. So his size is to scale of how much of our brain is dedicated to that part of our body, both for motor function and for sensation. So notice his lips, his tongue, those are enlarged, his ears, His hands are very enlarged, right? So we really need to do a lot of precise things with our hands, for speaking, our lips and our tongue, right? So those things, and coming up with neural prosthetics. So they put this little aspirin-sized device in someone's brain, and the person can think about drawing, can think about changing the channel on the TV or playing a video game, and the prosthetic, the robotic arm or whatever, learns how to do that by following what the brain. So continuing on, so the somatosensory cortex, say that 5 times fast, that is right behind our motor cortex, but the motor cortex is in the frontal lobe, and this is in the parietal lobe. So parietal is for touch. Remember, you're shampooing your hair. So if you think about that in the key function of body touch and movement and sensation, that is really what the somatosensory cortex does. You can go back to homunculus here too and talk about the somatosensory cortex and how much brain space is set up for that, because it's the same thing we're talking about, even though they're 2 different parts of the brain. All right, so the prefrontal cortex is very similar to thinking about the frontal lobe. So think about planning ahead. So the association areas. So this can be a tricky topic just because this is a complex part of our brain. So when we're talking about these lobes and we're saying, oh, there's a spot here for voluntary movement and we can map that all out, right? Well, there's these other parts in all 4 of the lobes that we can't exactly. So association areas. So they're above the cerebral cortex, but they're not involved with primary sensory or motor function. So they're not a direct thing, like I just said. So they're for interpreting, integrating, and acting on sensory info. And they're also linked with memory. So that's another important part of it. So talking about association areas in all of these lobes, well, there is a case study from a while ago, right, from 1848, about a railroad worker who was working on the railroad, and he was packing his gunpowder, with the rock, tamping it down, laying railroad, and it exploded. The gunpowder exploded, and the metal rod went, and this is a picture of him, went through his cheek and out his skull, and couldn't see out of his eye after, and he lost a teacup size of. He was immediately awake and alert and talking. So people were so confused and astonished. They thought for sure he would die. He didn't. They took him back. The doctor didn't believe him that he actually had lost brain, or that this had happened, because he was like, you're awake, you're talking, like this couldn't have happened. But it did. So he kind of changed, though. He wasn't the same Gage. He was no longer Gage, his friend said. His personality changed. He became a little more impulsive. He was quicker to anger. He was just not the same. So what this shows us, because remember, case studies, we can't generalize everything, but we learn things from case studies. So they learned from this case study and from other case studies that these different parts do different things. And for him, this prefrontal cortex, that is our judgment, planning, thinking ahead, right? So our emotional control, our impulse control, that is our frontal lobe. And we see that through other things too. But Phineas Gage was kind of the first look at well, first of all, you can lose a teacup size of brain and still be functioning, but you're a little different. Phineas Gage's case comes up a lot just because it's a very famous case. It's one of these first case studies that they looked at to realize that different parts of the brain have different functions. Okay, 2 more parts of the brain. So Broca's area and Wernickes' area. Broca's area is in the left hemisphere of the brain, because the left hemisphere is responsible for speech production, and Broca's area is the specific part of the brain responsible for speech. So the trick to remembering this is I would like you to picture a talking doll. Hi, mama. Rip its head off. So a broken talking doll, Broca's area. So think Broca's area, broken talking doll. A broken talking doll cannot speak. A damaged Broca's area cannot speak. Wernickes' area is the portion of the brain responsible for understanding, comprehending language. So this can be confusing when they do this in an applied type scenario. So I gave you 2 examples here. So if a patient can talk, but the words that come out do not make sense or they do not form full words, that would be a problem with Broca's area. If the patient cannot understand language, they can talk. Now, obviously, because they don't understand language, what they're saying isn't really making a lot of sense, but they're able to produce words. That is a problem with Wernickes' area. So finally, plasticity. Let's talk about this. Our brain is able to modify, adapt, and change. People have all sorts of brain injuries, trauma, and they're able to come out of that and grow and kind of rebuild and do things that they were once able to do. Not always, and maybe not all completely the way they were before, but our brains are able to do this. And in childhood, our brain is doing this a lot more than in adulthood, but it does happen in adulthood. They used to not believe that. Neural tissue can reorganize too. So when we are talking about people who are blind and deaf, for example, the portions of the brain that aren't being used, like for example for the blind, the visual cortex is not being part of your brain for touch because of Braille actually expands into the visual cortex because you're using your fingers more for Braille, so that part becomes stronger or takes up more cortical space. Deaf people have a similar thing where they have enhanced peripheral vision, and that comes in as the visual cortex invades the temporal lobe. So those things can happen. Also, if someone has had some sort of injury, they can learn to walk again, they can learn to write again, they can learn to speak again if they've had a stroke, right? All of that, I know a lot of times when it's limbs, we think about teaching the muscles, but it's really about teaching the brain after a brain injury to do those things. They have also found these master stem cells, which is very interesting because these are what they believe are associated with neurogenesis. We haven't been able to use this in any way yet, but think about the ability to help someone restore a part of their brain for whatever reason through using master stem cells. Your cerebral cortex, that's the higher, most evolved level, is that thin layer over our brain. Don't forget about glial cells, the little worker bees helping all of our neurons. And know the 4 lobes and the functions, so try to remember the things that I was telling you as little tricks. Your motor cortex, think voluntary movement. Prefrontal, think like frontal, so decision-making, judgment, which, by the way, isn't really fully developed until you're closer to 30. Association areas, so that's higher level thinking. They're more complex, higher level. They associate, they integrate everything together. Don't forget about Phineas Gage and his chunk of brain that he lost. That case study does. When you think about Broca, think broken doll. Then remember that our brain can modify and grow, and it can grow new baby neurons. All right, so I hope that this was helpful to you, and I will see you